What we are able to do now is answer the following question. I'm at a certain point in the structure. There's a certain state of stress that I'm able to calculate based on, say, Me 231 knowledge. And that state of stress is with respect to some convenient set of axes, which gives me the original picture of the stress, its geometric depiction. But now what I'd like to do is I would like to, at the same point, be able to calculate the components of the stress, in other words, the geometric representation of the stress that is rotated with respect to the original picture. I'd like to be able to calculate those components based on the original components, and those are the equations that delivers me that. If I know sigma x, sigma y, and tau xy prime, these equations deliver me the new components of the stress on that rotated picture. It's the same state of stress. However, I'd like to be able to do that. Remember why? Because our motivation is going to be eventually the following. Suppose I know that this point in the structure is a critical point, and I would like to eventually determine whether failure occurs there or not. And I know, for instance, that this is a metallic material, so it's going to eventually fail if at that point the shear stress that I find exceeds a certain value. Now, I can look at the original picture and calculate the value of the shear stress, but I cannot conclude that at that point, if with this picture tau xy is below a critical value, then I am safe. I cannot conclude that because I know that if at that point I had taken a different picture, in other words, I had taken a different plane, I looked at a different plane, then the shear stress possibly would take a value that would be different and therefore perhaps larger than tau xy. So tau xy prime could be larger than tau xy. And therefore, at that point, if failure occurs, it's not going to occur on that plane, but it's going to occur on a plane that is rotated with respect to the original picture, right? So therefore, I have to search all possible surfaces going through that plane, in other words, all possible pictures, in other words, all possible values of theta, and find the value of tau xy prime among all that is the largest, let's say. And that value of tau xy prime will be the one that will determine whether failure occurs or not necessarily that one, right? And alternatively, I could have a brittle material, and that material, at that point, it could be a critical point, because the normal stress is going to exceed some critical value. And now, however, if on that picture, if sigma x, say, is less than that critical value, say it's larger than sigma y, it doesn't mean that this is a safe point, because I know that if I take different cuts, different orientations, there might be a surface going through that point on which the normal stress is actually going to exceed the critical value that the material can sustain, so I will have failure. So I have to again search all possible surfaces, all possible orientations of this picture, of these surfaces, and find the normal stress that is the largest among those, and compare that against the critical value, say, that the material can sustain. So that's why we're doing this exercise, obviously not for fun, because ultimately failure is going to be occurring on some surface that I can identify through this analysis. And notice always that I'm not rotating the structure. I'm always at a given point in a structure. There's a certain loading. I'm looking at a critical point, and at that point, I'm just looking at different surfaces. On every surface, different orientation, there will be different normal and shear stresses, and those will govern ultimately failure. So now, let's go back to the question of searching all those orientations and finding the largest value that I can possibly find. If we want to do that rigorously, we can just do an extremum analysis, and that's what we are going to do. And we'll start with the normal stress. So it turns out, notice that x prime and y prime, and for that matter x and y, they just differ by an angle of pi over 2. Or from now on, I'll just refer to in degrees, if you like, an angle of 90 degrees. So I can work with one and always find the other by taking into account that there's going to be a difference of pi over 2 between them. Let's keep that in mind. I'll focus on sigma x prime and eventually together with tau xy prime in the following analysis. So first, I will start with the normal stress. So what I'd like to do is search all possible values of theta and eventually among those find the extremum values. Those extremum values will be called principal stresses. Okay. So first of all, I take sigma x prime and I notice that it is a function of the orientation of the cut that I'm taking, which is identified through theta. So now I want to search the extremum value. Now that extremum value, when I do it mathematically, might deliver me a min or a max. I don't know yet. We'll see eventually what I get. I might be interested usually in the max value, but depending on the sign, the minimum value might have an absolute value that is larger than the max value, because min and max also takes into account the sign. Right? So now I want to find the extremum value. This is a function of theta. How do I find? Well, I can take its derivative. And when I take its derivative with respect to theta, well, it is not necessarily going to be equal to 0. It's going to be some function. Let's go ahead and take the derivative of that function. And that the derivative is going to be so it is sigma x minus sigma y over 2 minus 2 sine 2 theta plus tau x y plus 2 cosine 2 theta. Okay. Now that's the derivative. Now among all possible values of theta, there will be a value that's associated with the extremum value. Let's call that theta n, such that when I plug in theta n, this thing will be equal to 0. Now when I set it equal to 0, I can go ahead and solve for theta n. First of all, I can cancel this factor of 2 that appears in the equations. And then I'm going to get, dividing through cosine 2 theta, I will get a tangent 2 theta here. So it's a tangent 2 theta n. Notice that because in the equations I have always twice the physical angle of rotation, the result also contains that factor of 2. And tangent 2 theta is going to be equal to tau xy multiplied by 2 over sigma x minus sigma y. Okay, that's the result. Now I can do the same thing, and I encourage you to do that yourselves. Sigma x y prime is a function of theta. I can again seek its extremum. We'll have a min or a max. Okay, and so I'll go ahead and take its derivative with respect to theta. And that is not necessarily equal to 0, but among all values there is a special value, let's call it theta s, such that this is equal to 0. Calculate what that value expression is, and you will get as a result an expression that tells you that 2 tangent 2 theta s this time, it's an angle that is different obviously from theta n, the way I denoted. So it's a minus sigma x minus sigma y divided by 2 tau xy. Okay, good. So those are the results. All right. Now, whenever you have such an expression, tangent of 2 theta, it will have 2 roots, okay? 2 sets of roots, and only 2 values are ultimately relevant and sufficient. Now, if notice that theta n is a solution to this equality, then theta n plus minus 90 degrees is also a solution. Okay. Now theta n is going to indicate one direction. The direction that's perpendicular to it is going to indicate another normal stress direction, which could be indicated either through plus or minus 90 degrees. So it's really the same thing. Same thing for theta s. It's going to deliver 2 planes that are perpendicular to it. One plane associated with theta s, the other one is plus minus 90 degrees. So there are 2 sets of solutions, and associated with 2 sets, if I take these and plug into the expression for sigma x prime and tau xy prime respectively, I will get corresponding expressions for the stresses that occur on these special planes. Those stresses, for normal stresses, they are called principal normal stresses. Now, when we say principal stresses, strictly speaking, this will become a little bit more clear in the future, but usually we mean just the normal anyway. But to clarify things at this stage, I'm going to call the normal stresses principal normal stresses, and here the values of the stress corresponding to these, the principal shear stresses. Okay, that is overall a terminology that we're not going to use a lot, okay, but let's keep that there as well. So the principal normal stresses will be indicated. So now we have x and y, sigma x and sigma y, we have sigma x prime, we have sigma y prime, and now because these are special stresses, we're going to indicate them with sigma 1 and sigma 2, okay. So there will be two results. I'm putting a comma because they differ by a plus or a minus sign at some point. Usually one goes with x prime, so it's a special direction x prime, which is direction 1, on which the normal stress is an extremum, and y prime is the corresponding direction for 2 is the corresponding direction for y prime, a special y prime direction, which is indicated with 2. But really, it doesn't matter what I call 1 and what I call 2. So at this stage, I'll just write the two possible values that you can observe, and those values are sigma x, sigma y over 2 plus minus square root sigma x minus sigma y over 2 squared plus tau xy squared. Okay. Now, on the other hand, the shear stress that I will observe, the principal shear stress, let's call it tau. Now, this notation might look weird at first, but so the principal stresses are associated with some new directions 1 and 2, and the remaining value is 3. I'm just going to call this 3. That's the way to denote the shear stress, the extremum value of the shear stress for me, okay? It really doesn't matter what I call this. I can call them sigma apple and sigma orange, and this is tau olive, right? It doesn't matter. It's just we're giving some names so that we remember what we're talking about. So I called it tau 3, 1, 2, and then 3. Okay, so 3 is not a direction. It's just a value that follows from 1 and 2. Okay, so that is equal to square root of whatever is in there, actually. So I have to squeeze it in here a little bit, over 2 plus tau xy squared. Okay, so exactly the same thing, notice. Okay, so in fact, even the plus minus part isn't there because, again, there will be two values, and it turns out tau 3, and I'm just writing 1, and I will write only 1 because it's sufficient to take only one, plus or minus. I know that if there's a plus, there will be a minus. It's easy to remember that. So when I refer to tau 3, the principal shear stress associated with all possible rotations, I will simply take the positive value. So, but there are, of course, two roots. One root is positive, the other one is negative. And here, likewise, there is an extension because this part plus minus carries over here. And so there is a part that's associated with sort of the average of the normal stresses, and then plus minus the principal shear stress. Okay, so those are the principal normal stresses, and those are the principal shear stresses. Now, there are a couple of things to eventually notice here. Now, the first thing to notice here is that there's something special about the picture that has to do with the principal normal stress. Now remember, what we are doing here is we are going ahead, starting with some original picture, which is a picture where there is a normal stress on both surfaces and there is additionally a shear stress. Goes without saying, there are stresses on the other surfaces as well. I'm not drawing that. Now then, I rotate these. I look for rotations, and I find very special directions, and those special directions are associated with principal directions. So I'm going to call those directions 1. So again, doesn't have to be the case that 1 indicates the rotation of x and 2 indicates the rotation of y, but that's the way I'm going to choose it to be. So this is a 2. Sometimes people mean with 1 the larger one plus, and 2 the smaller one, the one with a minus. But presently, so I'm assuming that we started off and the axis rotated by a certain amount theta n, that's spatial rotation. Now that spatial rotation gives me 2 axes. How do I know that there are 2 axes that are called 1 and 2? Because those are my principal directions. On those directions there will be stresses 1 and 2, and those directions differ by an angle of 90 degrees. These do differ by an angle of 90 degrees. So I know that those are the 2 special directions. One and another one that differs by pi over 2. And therefore, I can go ahead and on that picture, I can draw a new expression for the way the stress looks. And that expression will have on the plane with normal 1, there will be a normal stress. And on the plane with normal 2, you see they just differ by an angle of pi over 2, or 90 degrees, there will be a sigma 2. So instead of x prime, we have 1. Why? Because it's a special x prime. Among all values, it's an extremum x prime, which we called 1. And among all y prime, it's an extremum y prime, which we call 2. X prime, y prime, x, y, 1, 2, they all differ by an angle of 90 degrees. Okay? So we are, remember always, we are looking at a point in the structure. We're always at the same point. It's just a different orientation of the axes. Now, you might be tempted to put a shear stress over there, but it turns out that on the orientation of the coordinate system or the planes that deliver you principal stresses, okay? So I rotated by theta n, I get 2 planes that naturally define a new geometric representation of the stress, 2 surfaces perpendicular to each other. And now I'm saying that the normal stresses are 1 and 2, that's what my derivation tells me, but there is no shear stress. How can you see that? Well, you can go ahead and at this stage take that expression and go ahead and do a small exercise and show that if you pick this theta to be theta n, so in other words, if the ratio of sine 2 theta to cosine 2 theta, you can divide everything through cosine 2 theta. This will give you tangent 2 theta, right? For instance, if theta is equal to theta n, then based on that result, you will show that the corresponding shear stress on these planes is 0. Okay? So on the plane where there is a maximum normal stress, on those planes associated with that picture, there is no shear stress. We have to keep that in mind. On the plane with maximum and minimum principal normal stresses, then we have no shear stress. Now let's go back and have a look at the way this picture looks. So we start from the same setting and we are just looking at now a different orientation. Now because it's a different orientation, let me attempt to draw it a little bit different as well. Somehow did look the same, but let's say that it was a steeper angle now. Okay. Now this is a new direction. I have no new directions. I don't know what the directions are. It's going to be some x prime, and it's going to be some y prime. Okay. But that angle is theta s, okay? And on that picture, I have a shear stress, which happens to be tau xy prime, which is equal to a extremum value, which is equal to tau 3, okay? So it's tau xy prime is equal to tau 3 because it's an extremum value, okay? Now, are there normal stresses here? Well, here, what you can do is you can take that theta s, tangent 2 theta s relation, and again go back to the expression that we had earlier, look at the normal stresses, plug in that special relation in here, and what you will find is that on these planes, the normal stresses are sigma prime y and sigma x prime, which are actually equal to each other, and both of them are equal to sigma x plus sigma y over 2. Okay, so on the principal planes associated with the normal stress, there is no shear stress. The normal stresses achieve extremum values. One of them is larger than the other, and respectively they are the largest and the smallest value that one can attain. Okay, and on the plane that is associated with principal shear stresses, the shear stress takes a maximum value, and eventually the normal stresses are the same as each other. Okay. So those are two observations that we can keep in mind. In particular, this one is going to be very important. Now, there are a few other things that we can deduce from these results. One thing that we can deduce is, well, you will notice that this expression appears here, rotate just 1 over that value is this one with a minus sign. And what I can remember, what we can remember from our trigonometry is that if we have an angle alpha, and if I go ahead and take its tangent, and I can add plus or minus 90, add or subtract 90 degrees to it, and the result will be minus 1 over tangent alpha. Okay, so in other words, the alpha angle here is referring to twice theta. Okay, you can either interpret it to be theta n or theta s. If to twice theta I add or subtract 90 degrees, I get apparently twice theta s. Okay, so from these relations together with this green indication, what I see is that twice the two angles differ by 90 degrees, or the angles themselves differ by 45 degrees. So theta n is equal to theta s plus minus 45 degrees. Not 90, but 45. So in other words, if on top of that picture I rotate by, for instance, an angle of 45 degrees, I will reach that red direction. Okay, that's what this is implying. Or I can rotate by 45 in the other direction. That's just as well. Right? That's what that relation is implying to us. That's also a useful relation, because in order to calculate these principal directions, I have to do some math. I don't have to do the same math again for theta. It's a trivial, small additional amount of calculation, but still, I don't really have to do it. Now, finally, what we can also observe is that you can go ahead and, at this stage, make an additional note to yourselves. What I see here is if I add sigma 1 with sigma 2, okay, so this expression plus or minus, they're added, that part dies away, I will get sigma x plus y over 2. So sigma 1 plus sigma 2 is equal to that added twice, sigma x plus sigma y. And in fact, if you go back to the expressions for x prime and y prime, something similar happens because they differ by a minus sign in some portions of the expressions, and therefore you will get sigma x prime, sigma y prime. Now, these expressions say that the sum of the normal stresses do not depend on the picture you're looking at, whether it's the original picture, some arbitrary rotation, or the rotation to the principal normal stresses. Always you get the same sum. Now, presently, keep in mind that sigma z is equal to 0. So if I add it to every expression, I add a 0. So in general, what this will eventually imply in 3D, it's correct as well. But I will state here for future reference in the future. For the future, I'm stating for the cases when sigma z is not 0. Okay, so I'll put here an exclamation mark to remind ourselves that I'm writing this without proof. So in general, sigma 1 plus sigma 2. In 3D, there will be 3 principal stresses, you'll see. And there will be 3 normal stresses. Those normal stresses are x, y, z with respect to the original picture or with respect to some arbitrary rotation. And normal stresses will always depend on the rotation in 3D this time, not necessarily in a plane, but in 3D some arbitrary rotation. And we notice that the sum of the principal stresses are associated with the normal stresses, are 3 times the hydrostatic stress. Okay, so eventually in the discussion of failure criteria, at some point, this is an equality that I will mention. Just keep in mind that it turns out that because of the underlying math, the hydrostatic stress does not depend on what type of planes you're looking at. You can either calculate it with respect to the original picture, some arbitrary rotation, or with respect to a principal picture. In all cases, you will have exactly the same value of the hydrostatic stress. Again, there is a big exclamation mark here that I should emphasize. So all of this is in a big parentheses. What we can presently rigorously show is this part alone. So this is a rather complicated slide that is, I hope, clear to a fair extent. We'll keep referring back to it. We're going to make use of the many observations that I've stated, and we're going to build upon it further.